Hello, welcome to my supplemental series on organic chemistry. Today I'll be talking about the two classes of reactions that we can deal with when we talk about mechanisms, which will be like things that involve Lewis acids and bases and oxidation reduction chemistry. The first thing I should probably talk about is what is a Lewis acid and what is a Lewis base. You all know that a Bronsted-Lowry acid and Bronsted-Lowry base would be something that accepts a proton or gives a proton. Well, our Lewis acids deal with electrons, and as we deal with organic mechanisms in general, we are going to be doing a lot more electron pushing. So a Lewis acid is an electron pair acceptor. Now a proton, H plus, still is an electron pair acceptor. So a proton is still a Lewis acid. Just now we can classify a lot more compounds as Lewis acids. Lewis base is an electron pair donor. Anything with a electron pair that is not currently engaged in a sigma bond can be a Lewis base. So OH minus with its negative lone pair is a Lewis base. But we're going to see a lot of other things being Lewis bases that aren't just OH. So a Lewis acid needs to be something that is lacking electrons. This is usually in order to make a doublet in the case of hydrogen, or an octet in the case of carbon, or nitrogen, or oxygen, or boron, or any of the p block elements. And in the case of metals, often we're trying to get to either 12 or 18 electrons, depending on whether you're trying to just fill the d orbital or the d and the p orbitals. But these two factors are going to control whether they are going to gain electrons or lose electrons. And so we need to consider all these things. Our Lewis acids now, oftentimes when we see things like boron that doesn't have an octet. We have metals such as, say, platinum and palladium and oftentimes zinc. When we have our iron tribromide and aluminum chloride, these guys are going to be Lewis acids. They are shy of the electrons they need, so they are going to accept electron density in order to stabilize those compounds. Oftentimes when we have metals partially oxidized already, these guys are going to act as Lewis acids. Our bases are still going to be largely oxygen and nitrogen with their lone pairs. It could be anything that has lone pairs, such as a carbanion, as we'll see a little bit later. Could be anything with a pi cloud, so like a double bond of some sort can be donating electron density. All these things are going to be Lewis bases. They're going to attack something else. Now, one thing we have to consider is when these Lewis bases attack, are they going to act as a standard Lewis base or a nucleophilic Lewis base? The difference between the two is that a standard Lewis base attacks only hydrogen, but a nucleophile attacks large nucleuses, like our carbon. So the question we need to ask is, which one is more acidic? Is the nucleophile in greater need of that lone pair, or the hydrogen in greater need of that lone pair? If the hydrogen is easier to access, or generates a more stable structure when it's removed, we'll often see the removal of a hydrogen. But if, say, carbon can better have the attack occur on it, we're going to see a nucleophile. So those things we have to keep in mind. And that's why when we deal with SN2 versus E2, we have to consider the bulkiness of the base.
As we deal with Lewis acids and Lewis bases, we're essentially seeing some sort of electron donation from the Lewis base into the Lewis acid. Now this could be a temporary donation, forming a temporary sigma bond to the metal, or it could be something a little bit more permanent, like when we form like water out of hydroxide and hydrogen. Essentially, like say aluminum chloride we have here. Pretend this is planar. As another chlorine comes here, aluminum has 2, 4, 6 electrons. It needs another 2. We have a chlorine coming in. It stabilizes this. Now, aluminum is supposed to only have 3 electrons. Now it has 4, so it has a charge, which allows this to be stable octet-wise, but unstable electron-wise. And so we end up having this able to leave again, but this is stable enough to hold this long enough to form the chlorine cation that we use in the nucleophilic, the electrophilic aromatic substitution. Now, we don't have to have just one pair. You could see the association of a double bond, that the electron cloud comes in and is going to essentially donate some of this electron density into making a sigma bond to the metal. It's going to be only partially associated because it then can leave again and be very stable. It doesn't have to essentially form this bond between these 3 atoms. Essentially we're seeing something like that when we see the association of metal to the double bond. So it's very easy to break off and reform our double bond again. And of course, we have various other Lewis bases, like this is NN-dimethylamine. We have this lone pair here. This could be associating with any sort of Lewis acid, like bind to the metal and break off again. Or it could also be serve the purpose of any sort of nucleophile, that this lone pair is coming in, attacking from reverse, kicking this sigma bond out as we're making a new bond. We kicked out the chlorine and replaced it. Now the question here is this hydrogen easier to extract than attacking from the back? And the bulkiness of this base and the bulkiness of this atom is going to determine that. If this is a bunch of, say, methyls, it may be a little bit too hard to get in close. It would be easier to, say, remove a proton from one of the methyls. But in this case, since it's all hydrogens, it's pretty easy to attack directly from the back. So that's what we need to do when we think about these. As you think about the steric bulk, you think about maybe resonance and stabilization, but essentially it's electrons attacking atoms that are shy of the electrons they need. Oxidation and reduction. are the other major mechanism we will see as we look through this. That oxidation is going to be our loss of electrons, our addition of additional oxygens to the compound, formation of new oxygen bonds, loss of hydrogen bonds, bonds to hydrogen. So as methane, which has its CH4 is oxidized, it goes to methanol, which now has 3 hydrogen bonds to the carbon and 1 oxygen bond. Goes to formaldehyde, which would be a oxygen carbon double bond and 2 carbon hydrogen bonds. Going to formic acid, which would have C double bond O with a single bond OH. So maybe only one CH bond. Finally, going to carbon dioxide, which has 2 C double bond O's. Reduction is going to be the opposite, where we're going to gain electrons. We're typically going to see a removal of oxygen bonds. We might see addition of hydrogen bonds as this occurs. And there always has to be a pair of the two as we see this mechanism. Are typically compounds that have a overabundance of oxygen. Oxygen being one of the key oxidants. But we also have things like peroxides and peroxy acids, compounds with the double oxygen setup. That we have our COOH. These guys are optimal for transferring a oxygen over. Ozone is another such case. It has an excess of oxygens it can transfer over. But we have many compounds such as osmium tetraoxide, potassium permanganate. These guys are fully oxidized compounds. They are optimal for giving some oxygens back. A lot of these compounds that we'll see do just that. Nitric acid is an example of an oxidant. HNO3 can go to NO2 and HNO2. Other oxidants include sodium hypochlorite, where the chlorine has a positive 1 oxidation state. Dichromate, where the chromiums have a 6+ oxidation state, and chromate, they also have a 6+. With the mixture of acid that just helps speed this along, but form chromic acid also with a 6+ oxidation state. So H2. But these guys are strongly oxidized materials, so they are going to be stabilized as they oxidize something else and get reduced themselves. Kind of like a potential energy curve, in that you roll a ball to the top of the hill and then it will naturally roll down, transferring that energy into kinetic energy. These guys are lots of oxygens. They are optimal for giving those oxygens to something else to stabilize. Many reductants, on the other hand, are things with an excess of electrons that wish to become positive. Things like hydrogen gas. When you turn a double bond into a single bond, we use hydrogen gas as the reductant. Sodium borohydride. We're going to turn boron from a borohydride into
into just boron again, a borane, by donating the hydrogen. Lithium aluminum hydride. These guys are technically also Lewis acid base scenarios because we're having hydride acting as a Lewis base, but it's also achieving a change in oxidation state when we use these guys in the presence of a proton. They're just a way of adding H2 across a double bond, usually between a carbon-oxygen double bond. But many metals we have, like sodium metal, pure sodium metal, pure lithium metal, or potassium metal. Sodium and potassium are often used to oxidize directly by just donating an electron. Donate an electron, a way to help oxidize a hydroxide, for example. When we add lithium, it's going to add between a carbon chlorine bond. Same thing with magnesium. Going to add between a carbon chlorine bond as we, well, this guy's technically going to do two equivalents of these are going to add. So you might R lithium and a chlorolithium. So we're going to oxidize the carbon. It's going to, well, I say reduce the carbon so it's more negative, and reduce the chlorine so it's more negative. But these guys are example of reductants. Forming a Grignard and forming an organolithium is an oxidation reduction reaction. That's what's happening. Oftentimes our reductants are going to be pure metals or things at a lower oxidation state. A common reductant is SOCl. This guy is going to accept some of these bonds. We have PBr3. This guy can accept oxygens and reduce something else. So guys that have some ability to accept some electron density, guys that are going to essentially act as a Lewis acid for oxygens.
The last thing I would like to talk to you about is a special class of oxidation reduction that occurs between a metal catalyst, where the metal acts as an oxidative and reducive intermediate. This is called oxidative addition and reductive elimination. It's where the metal changes oxidation states. Oxidized to form two bonds to the compound, and we see the formation of two new bonds as it's reduced off again. So we have, say, a metal here that has some extra electrons laying around that it can give up, and we have a compound with a bond that needs to be broken. This is what we're going to see in things like the Heck reaction or Suzuki coupling, where we're essentially coupling more than one compound together. Essentially here, we're going to break this bond and break this bond to make two new metal bonds. We have a methyl attached to the center metal, and we have, say, this chlorine or whatever attached to the center metal. The metal has lost two electrons to make this is a minus, this is a minus. And now the reductive elimination, we can make a new set of bonds. We break this off and we exchange this around. So that, oh, hey, now instead of a chloromethyl, maybe this is a bromomethyl. The metal has gone back to its original oxidation state. We've just changed the bond attachment. Many different things where we have a metal catalyst in the center. This is what's going on. You don't need to know exactly what's going on, but this is an oxidation reaction. We're bringing the metal in, binding there, and then kicking it off again and reforming the catalyst. That's what we're doing when we do some of the, say, like, some of the crazier reactions out there. That concludes my video. Thank you for your time. Hopefully this helped explain a lot of the mechanism, the basic class of mechanisms of Lewis acids and bases and oxidation and reduction. Almost all of the mechanisms will have some combination of these two. So if you recognize one, you can kind of see where it's going. Hopefully this helps.